You're getting fast with those YouTube links there, Matt.
Slowly, yeah. Oh, maybe Discord is making noise. Something's been beeping on my computer, and it's always a little short beep, and I can never figure out what it is. Maybe it's Discord.
We can't hear it, thankfully.
Okay, see if that works. And let's record. All right, we are now live. Welcome to Thursday. And today we are going to be talking about teamwork. I asked you to read a couple of articles, but before we get to that, I would like to talk about the exercises. So hopefully you've received the grades and comments in eClass. But let's see. So the first exercise was looking at the interactive training. It seemed like some people seem to enjoy that. And the second one was the active learning part. And I thought Tobias did a really pretty nice job with his video, and I was hoping he could tell us a little bit about what he ended up doing for that part and why.
Yep. Can you hear me?
Yep.
So basically, the idea or what I thought about how active learning works is you're trying to get some measure of how confused the model is about the data that it's given, but it's not necessarily related to the error or the loss or what have you. It's more interesting to do something based on dropout. So what I did was I took a model and trained it using, I think, I don't remember exactly, but about 40% dropout. And then when I ran inference on it, rather than turning the dropout off, I left the dropout on and did the inference, again, I don't remember numbers, a certain amount of times. So basically the idea is that the more frequently a path gets reinforced, the more likely it is to pick up across the dropout. So you get this kind of notion of confidence that carries for your network at the cost of having to run inference X numbers of times. So that was basically how I did it. And then I returned the samples either with or without replacement to the data set and let it retrain.
Yeah, and that's a common trade-off, figuring out how to trade computation for less data or better results. Because in a lot of AI problems, you can get the right answer, you just don't have time to get there.
Yep.
Cool. So that was exercise 1, and then I wanted to talk a little bit about exercise 2. So it seems like it seemed like there were no major crashes with HippoGym, so I was pretty excited about that. Good job, Nick. So we asked you to kind of basically mess around with HippoGym. That was the goal of this assignment. So then there are a few questions. What types of applications could this be useful in? Something about the demo, interpretations. But then I asked this really open-ended question where we were saying that, the maximum frame rate could be too fast. So I thought there were a few pretty interesting ideas. So I wanted to pull out a few of them. So for anyone who wants to jump, is anyone willing to talk about the ideas that they had for exercise 2? Or because this was so long ago, I'm happy to just talk through it all. Okay, feel free to interrupt or correct me if I get it wrong. But one Tobias's idea was thinking about time warping. So remember in one of the crowdsourcing papers, Walter's paper, they were changing the speed so that people could better caption audio. And Tobias was saying, well, what if you could kind of figure out when the human was most likely to give feedback, or maybe where feedback would be most useful, and kind of slow down then. And I like that idea in part because we implemented something a little bit similar a few years ago, where we had an agent that was getting trained by a person, and that agent, the speed of the agent depended on its confidence. So when it was uncertain, it would slow down, kind of prompting the human to give more advice where it was most useful. And then Reven also had the idea of modeling the human, but instead of trying to figure out when the human would give feedback, you could actually try to use that model to train the agent. So if you could know when the person and when and how the person was going to give feedback, then you could try to use that model instead of just relying on the human. He also mentioned that you could try to augment the MDP's reward based on that feedback, which I think a few other people mentioned. Bradley mentioned a similar time warping idea, but he also mentioned changing the speed on uncertainty. And one idea he had was to let the person go forward and backward in time, which is it's in some tasks that's easier or harder to do. So if you're just have an agent that's playing a game, maybe you can pause the game pretty easily or slow it down or speed it up, or maybe you can even go backwards. But if it's a robot, that's probably a lot harder to do. So if you've got a robot playing ping pong, it's harder to tell the robot to back up to a particular state. But if you had a video of it, maybe that would be sufficient. You could go backward and forwards in time with the video and then use the video to find the right state to give advice on. And then Spiros had a few ideas. One was to learn a critic. So in the actor critic framework, you've got something that's taking actions and the other that's criticizing it. Well, if you could have a human teach a critic, then you could take that critic and the actor, go onto a cluster and run at superhuman speed. And that's an idea I'm pretty excited about. I have one student who's working on something that's a bit similar, but so far we don't have any results yet to know whether it's a good idea or not. But other ideas, we're also thinking about incorporating multiple humans, because if you've got more people giving you advice, then maybe the not being able to give much feedback based on the speed isn't that big a problem. And he emphasized that, well, you can really focus on what humans are good at. So if I interpreted this right, he was saying that, well, if the task is really fast, maybe this is not the right modality for the humans to be interacting with the agent to try to help it. The other thing I wanted to mention, there was also, oh no, I guess it wasn't an actual question. A bunch of people ended up asking, so how exactly is the agent learning from my feedback? It doesn't seem very good. And you're right, it was not good. It was not learning. It was completely ignoring your feedback. And so sorry about that. I would have liked to have something working that you could have tried out, but I decided it was more important to get Hippo Gym in front of you and play with it rather than waiting for us to get the algorithms implemented the right way. Luckily, we do have a few students who are working on that. So, and hopefully in a few weeks, there'll be a version of Hippo Gym that use Tamer, one that uses Coach, and possibly a third algorithm. So if you'd like to see how easy or hard it is to teach an agent, I can give you that link and you can mess around with it. It's actually kind of cool because I was teaching mountain car, and it was learning in about a minute. Mountain car is not that difficult a task, but it's still pretty cool to be able to teach it something that quickly. So any questions or comments on exercises 1 or 2? I'd be particularly interested if people thought these were useful or not, because the goal of them was to try to get some hands-on experience, start messing around with some stuff so that it wasn't that you didn't do anything except the final project. But I'd be really interested in your feedback on whether you found these exercises worthwhile, if they took too little or too much time. Does anyone have any feedback they'd be willing to share? You could also drop feedback in the questions and comments about Matt's lectures channel. if you didn't want to unmute. Ooh, tough crowd today. Oh, thank you.
I mostly thought they were pretty fun. The teachable machine was a good introduction to supervised learning. It's easy to see how it works and see how things go. And the other portion was fine too. It was a good length. I guess I found both tasks to be a reasonable length. Then neither required particularly too much knowledge about any given topic, which I know is kind of tricky to get right. So no, I found them useful. They were good.
Okay, thank you. Because you're right. Since the prereq requirements for this class are pretty lax, we've got very different people with very different backgrounds. So I wanted to try to make them accessible. Any other? Yeah, Reven.
Yeah, I thought they were both like good length, not too long or anything like that. I think I preferred exercise 1 over exercise 2 just because it had some programming and it was cool to like actually implement some of the stuff we did in class. Yeah, so those are my thoughts.
Great. Yeah. Actually, now that you say that, I think what I would like to do next time is say, here is most of a tamer agent in HippoGym. Please implement the tamer, the missing lines of the tamer algorithm, and then and then show me you can train it. I think that would probably be better.
And then the agent would actually learn.
Yes, if you code it up right.
I think honestly, I might be in the minority here, but I think another assignment would have been fun as well on some of the more stuff later on in the course that we were doing. And also, I really liked assignment 1, although the blog post did have some errors, if anything.
Really?
Yeah, there are a few parts that were that didn't really make any sense in terms of like Python code.
Yeah, there's some really
besides
hacky
that-
stuff in there.
Yeah, some real. Yeah.
Okay.
Yeah.
Yeah, I think they trained on their test set and stuff like that as well.
Yeah.
So next time I do exercise 1, I could say, here's a blog post that's not quite right. Can you identify the errors?
I think your idea for mostly implementing like the tamer or something like that is nice, because then you don't have to spend as much time focusing on all of the like all the details beyond the actual algorithm, like getting the data to work and getting the environment set up and that.
Exactly. Yeah.
Yeah, I wanted to mention on that same point, kind of like the teachable machine stuff is really nice, like quick high level understanding of like, oh, if I give more data, this is helpful. If I add more classes, it's hard or it's harder, as opposed to like having to implement everything, I guess, from scratch. It might be a lot easier right away. And the assignment or exercise 2, I think was just cool to see what giving human feedback is like, because as much as you read, like we discuss it and stuff, I feel like until you actually try like giving feedback and seeing how the user interface might actually affect this a lot, or like if you can't use arrow keys and you have to actually click the different arrows, is a big difference in terms of human quality of feedback. So there's like, I don't know, a lot of things that maybe you don't really know until you try it yourself. So it's nice to get something to work like that right away, as opposed to having to like try implementing something from scratch, which would take forever for something like that.
And that's a great point. Like we all know user interface is important, but until you try to train an agent by clicking on buttons with a mouse versus using the keyboard, that really kind of brings it home. And I like the suggestion from Rohan that you could turn this into a competition. So thinking about who can train the best agent, or who can train an agent to reach this performance with the fewest number of pieces of advice. So in my winter class, traditionally the class it's mobile robotics, and usually the class is taught with a competition. And Laura is going to be one of the TAs, and we've been talking about whether it makes sense to do that competition, because on one hand it's really fun and is quite motivating. On the other hand, it's not motivating to everyone, and it's anything where your grade could be improved by someone else's failure just rubs me the wrong way. But I know students often like competitions and they're fun. So the other thing I wanted to mention is that I see the chat of Zoom is bouncing up and down. Yeah. This is my first grad class at U of A. I am guessing that the workload for this class has been less than average. I'm guessing most grad classes assign more work, but I've purposefully been keeping the workload low because I expect that you'll need to spend a lot of time on the project, the pilot, because you've had to spend time trying to formulate your hypothesis and pilot study, and then you're going to program stuff up, and then you're going to run human subject experiments. And because I know that is going to take a significant amount of your time, and I know that when you help other people run their studies, that's also going to take some of your time. So I know it's not ideal to say, well, I didn't give you much work at the beginning of the class, so the second half of the class is going to suck. I know that's not very helpful or fair, but I did try to reduce the amount of things you had to produce. So I liked that people had the option to do extra investigation, and some of you did on the exercises. Similarly, when you read a paper, you could just read a paper over in like 45 minutes or an hour, or you could really dig into it when you find it exciting. And someone asked, is there an exercise 3? Yes. So there is an exercise 3. It's based on what Anna presented last week. I am working with Hager to make sure, what's the right way to put this? Anna had a really interesting idea, but it wasn't fully fleshed out in terms of what exactly students were going to produce and how they were going to do it. So I'm working with Hager to make sure that we can kind of make sure we understand where she was going, and that the exercise will be, roughly on par with the other ones. So I'm hoping to get that out today or tomorrow, and you'll have some time to work on that. And then I'd still like to come up with an exercise 4, because I've asked everyone to do at least 2 of these exercises, but I know some of you have seemed to enjoy them, so I'd like to give you another option. Or if you were late or had to miss the earlier exercises, I'd like ideally to have 4 options for everyone. So if you have any suggestions for another kind of exercise, particularly if you had a suggestion for a kind of exercise which would help your project, I'd be really interested in hearing about that. Which also comes back to future topics. So if we go to the course webpage, we can find the course webpage. No, can't find the course webpage. Okay, so on the course webpage, you'll see that we are finishing up the teaming section. And then after reading week, there's time for some class interests. So I'd like you to start thinking about what kind of things we can do in class that would be interesting and ideally useful, either to your research outside of this class or your project inside this class. So you all have come up with a bunch of really cool ideas for your projects. You've hopefully already started doing some background reading. So if you think there are papers that would be of general interest or would be helpful to you, I'd love to be able to use those weeks for that. So start thinking about where else this class should go in terms of topics of what we do. And I also wanted to mention on next week, we're going to have one class about kind of ethics and dangers. So I'm asking you to read about Theorem 25. Hopefully you've heard of this before. This is kind of a tough paper. It's not it's not that complex. It's not that long, but it's emotionally draining, I think, is a way to put it, because it's forcing you to think about how your system could have real world effects and how that could have deadly consequences. And that's true of many parts of computer science, right? Because we're building software and sometimes there's bugs or someone hacks it or something happens. So when you are building software that can take or influence important decisions, things can go wrong. And that can be extremely true with AI systems. So I would like to spend one class kind of talking about the ethics of AI. I am not an ethicist at all, but I find the topic interesting. And I think every computer scientist should at least have some experience thinking about these kinds of things. Okay. I think that's everything. Any other open questions or comments? All right, so let's see if I can do this now. Okay. I figured out how to make a custom Zoom poll, which I used to know how to do, but then Zoom again changed the interface, so I had to refigure out how to make a Zoom poll. So I asked you to read 2 papers today, and we probably won't have time to get through both of them. The first one was talking about human AI teaming, and particularly the importance of how changes to the AI can influence the team. And the second one was thinking about how could we use machine learning to better help a group of humans work in a team. So it's kind of a different take on that human ML interaction. Okay. 50% voted. I'm going to stall for a few more seconds in case other people have opinions. All right. So hopefully, just like the US election next Tuesday, we have a landslide. Okay. Done. Yeah, I am pretty nervous about the US election, but that's a different story. Okay. So I have not prepared any slides. I was hoping that we could just kind of talk through the paper so that kind of say what the paper was about or what people found interesting. So would anyone be willing to take a stab at the high level description of the paper? Or maybe one, or even one of the people who voted for the paper, maybe they'd be willing to say what they could say, even why they found it more interesting.
Did you say which paper we're doing?
Oh, sorry. I thought you could see the polling results. There. Now that I've correctly shared the results, you can see that 10 out of 11 people voted for the updates in human AI teams. Can you see the results?
No, I can't. Yeah.
Okay.
Awesome. Out of a total of 101% people.
Yeah. Okay. Good. So we're going to be doing the this one. So it's another paper that has Ejay Kamar, Walter Lasecki, and Eric Horvitz. We've seen their names a few times before. So of the 10 people who voted for that paper, why did you find it interesting? What did you like about it?
I can start off with just mentioning the one point that I never thought that, or I guess it's maybe I did think about it, but it was just fascinating that like an update that actually upgrades performance can be bad in a sense that it like negatively affects the human. So like if we just update the AI and it's like, oh, the performance is way better, obviously this is better. That might not be true, which like intuitively kind of makes sense. Like if it improves in a lot of places, but then kind of breaks in a bunch of places, or like in a few places that the human really thought were important, it's like, oh, I'm really going to lose trust in it now there. So that can break a lot. I thought that was just like a point that never really crossed my mind for some reason.
Well, and like Google just improved all of their icons. So now when you look at Google I can't tell the difference between Google Calendar and Google Inbox when they're just small tabs. So that they thought that was an improvement, which I think kind of broke the system. But so Vlad's point was that they make the AI better, and that makes the whole system worse. And that's kind of a counterintuitive result until you start thinking about, it's a partnership. And especially in cases where the AI is assisting the human make choices and the AI is not perfect, the human needs to understand where the AI is not perfect. David actually, before we go into negatives of the paper, are there other positives, things that people liked about the paper?
I really like how they formalize trust as humans' mental model of AI, because it seems like such a nebulous concept, trust, and it's really nice to see them sort of nail it down and then work on that.
Yeah, so often people will do a 5-point Likert scale saying, do you trust the AI? Very much, a little bit, I don't know, no, and not at all. And yeah, but okay, I guess you can make relative comparisons then. But if you formalize the model, then you can actually measure that. So I read this, I don't remember, maybe yesterday, so long ago. So what did people think of the mental models? Because I know I won't call anyone out, but I know some people are thinking about modeling how AIs model people, and I'm curious if anyone thought whether the models they were using, the way they were modeling the humans, was good or realistic or useful. Okay, well, maybe we'll come back to that when we drill down into the details of the paper. Were there other things that people did like about the paper, just in general?
I thought the whole approach with the hidden, because when I first started reading it, the idea that they were going to hide features from the human, I was kind of turned off by that. I thought that was weird. But then as I grew to understand why they were doing it, it's kind of like, well, you have to trust the AI to do some portion of the task that you don't understand. And I thought that was clever, the way they were trying to hide a portion of it without hiding all of it, and getting the human to try and recognize when it was likely to be right and when it was likely to be wrong, kind of thing. That was clever.
Yeah, because they specifically made it so that a person couldn't do well on their own. They had to rely on the AI. And in the human computer interaction or the human AI interaction literature, you often see these kinds of clever experiments. Whereas in machine learning, it's often, well, I ran the thing on a data set and does better, end of story. Whereas if you can come up with more clever or more useful experiments, you're better able to measure and understand things. So, David, why didn't you like the notation? What in particular could have been improved?
I guess I got quite confused at how they overloaded the definition of their loss, especially the second time they used it, and that confused me a bit when they were defining what is this? Equation 4 describes imitation dissonance. When they were describing imitation dissonance, I was like, oh, like why is loss taking in a function when it was defined as something else before? Yes.
Yeah, so I found the D prime, the D double prime a little bit awkward. But I did like, so when I read a paper like this, I always read the English and try to understand that and then go look at the notation. I know not everyone does it that way, but I really appreciated them having clear, concise English definitions. That made it much easier for me.
Yeah, that was kind of the only way I kind of understood what they were doing was from the English. You're totally right.
Yeah. And then do you want to mention what you were talking about, the discrepancy between mental models?
Yeah, I mean, it just related to the earlier point you brought up I think Scott brought up, where it was really interesting how they basically found a way to measure, I guess you could call it trust in a system, which is through this lower performance based on this discrepancy of this mental model from one update to another, which I thought was pretty, like, was an interesting thing to think about. Yeah.
Cool. Okay, so why don't we go through this in a little more detail? So the basic, and please jump in when I say something wrong, or you can add. But I think the basic idea was they're talking about AI advised human decision making, and how if you've got an AI, you might want it to learn. That seems kind of obvious. But if the AI is helping the human in this advising way, changes to the AI, even if they improve the AI's performance, could be detrimental to the team. I think that's really the core contribution. And then another contribution they had was kind of developing this platform where you could partake in these types of studies. So if this was something exciting to you, hopefully you'd be able to bootstrap off of their code, and you've got this concrete domain that you could study this kind of thing in. But they did also use the real world data. So that was nice. So then what did people think of the AI advised human decision making with the S1 through S4? Did that make sense? So let me rephrase the question. I looked at this and said, wait, this is a reinforcement learning problem. What the heck is going on? Because they say the environment provides an input, the AI suggests an action, the human makes a decision, which is essentially an action, and then the environment returns a reward. So I'd like your opinion. Is this an RL problem, or is this a supervised learning problem, or is this something else?
I guess framed this way, it could be RL. I mean, it's also kind of Markovian as well. But I guess it is a bit confusing because they like frame everything else as a supervised learning problem with like a regularizer, essentially, right?
Can you remind us what you mean by Markovian?
As in like your current state, your current, everything you need to know about the environment is encapsulated in the current state.
Yeah,
essentially.
Yeah. So basically, having a full history, remembering past states won't help you. Yeah. So it seems like they're saying the human is a reinforcement learning agent, because the human sees an input, gets advice from an agent, and then makes a decision and gets a reward. But it also depends on what those actions are. So if the human takes an action and that influences the next input, then it's likely reinforcement learning. If the human takes an action and it doesn't influence the next input, then it could be more of a bandit. Or if there are only two actions, and after the human takes an action, they are either right or wrong, then they are provided a label, and then it might be supervised learning. So I don't know. Did any other opinion? Yes.
I think they are making assumption that human cannot justify the decision that the machine is making. So like in their experiment, they hide some feature from human. Yeah, that's why I think, right? So you may need a reinforcement learning. It's like a reinforcement learning environment. You have to try and see what's happening. But I think maybe in real case, you don't really have to try this and see what happening. You can just justify if this decision makes sense and you choose where to use it and you build your own model, trust model.
Yeah, because in one sense, this is a partially observable environment because they are hiding some of the dimensions from the human, and the human could try to figure out what the hidden state is, maybe figure out what the hidden state is by interacting with the AI, or the human could so in that sense, the human might be able to just take actions without needing the AI. Or I think in this particular case, basically they say the human can't do that. They have to rely on the AI, so that they're claiming that the human has to model the AI in order to perform well, so that they know when to trust the AI and when not to. But I'm not sure I understood the problem setting well enough to fully understand that. But based on the authors, they probably did it right.
I had a question about the setup for it. I think at one point they say that when they're using Mechanical Turk, they explain to the Turkers what exactly is being tested. Do they tell them that they do not have enough information to solve this themselves, or are they just told there's an AI that will help you learn off the AI?
Yeah, that's a great question. So I did not see the actual instruction they gave the Turkers. I'm not sure if that was in the paper.
Yeah, unless I missed it. It was kind of, I guess, just like for the group. Did anyone see something I missed? It seemed like they just said, and we told them about the experiment.
Well, what do you think? What would the differences be between those two scenarios?
So certainly for the beginning, I would be immediately distracted with trying to solve it myself. Like there's a little dice game that I was introduced to recently. It's called Petals Around the Rose, and you roll 5 dice, and then if you're playing with someone who knows, well, you have to be playing with someone who knows the game, they'll just tell you how many points that is. And you have to start building a model of, okay, why is that roll 14 points when something that was really similar to it last roll was 2 points, kind of a thing. And it's very funny watching people, because they start to build a mental model of, oh, I add everything up and then divide by 4 and then round up to the nearest 5. Like they get this really complicated version of what the game is supposed to be, and it's almost always wrong. It's a very simple little thing. And had that game been changed to, you do not have enough information because I'm also keeping 1 die in my pocket, and that's actually, it's just like whatever the roll of that die is the answer, I feel like I would just break some people, like just not being able to get the answer yourself.
Well, and for when we talk about mental models, or in the other paper where the team is working together to solve a problem over an hour or two, I always wonder how much effort are people putting in, because the average Amazon Mechanical Turker is not going to have an advanced degree in computer science, right? So my mental model of them is probably wrong. And how much effort are they really going to put into it, and what is their capacity? So like in the pedal example, it's also quite possible that even if it is a simple rule, there are some people who would not be able to find it before they decided to give up. And I'm not exactly sure how you account for that in experimental design. So to make that a more concrete thing, so let's say you're running an experiment, and it's going to take around 30 minutes, and some people will just give up and quit. after 15 minutes because it's too hard or it's not enough fun. So now you've got a self-selected group, and what biases does that group have versus the general population or versus computer scientists or versus the average Turker?
Yeah, that's a good point. And then also, for many of the real life applications that you would want to do, it's experts whose time you are not able to get. That's part of the reason that you're creating the AI system. And so what biases are there in that direction towards what you actually want to know about? Like how much better would a group of computer scientists or lawyers or doctors or whatever perform on the task?
Yeah, so maybe that's a really salient point, that if a certain group of users is going to be actually using the system, you better be training on that same kind of person. You want to train and test on people who have the same qualities or same capabilities or patience.
So I did wonder about that. I know we were talking about this paper, but with the team paper, I did wonder about how the results could have been radically different if you had different populations rather than Mechanical Turk.
Yeah. So if you had a bunch of, I've been friends with a few different lawyers who are extremely competitive. I don't know if that's all lawyers or just I have a biased sample, but I could see a group of 5 lawyers versus 5 normal people behaving very differently and getting very different outcomes, regardless of the management structure of the team.
I guess that turns into a question, like what kind of representative sample are like Mechanical Turks, the people that do Mechanical Turks, right?
Yeah, and there's been studies on that. The short answer, so this has probably changed. So the last thing I read a few years ago was saying that Mechanical Turk is not very representative. It is more English speaking, more North American, I think wealthier in average. But if the baseline is running your experiments on freshmen who are enrolled in a psychology class and have to do experiments for credit, Mechanical Turk is much better. So I think one way you could help. So in reinforcement learning, there's this idea of important sampling. So if you're doing off-policy stuff, you can reweight to better evaluate different policies. So I wonder if there's a similar thing here, where if we say, I care about this working for normal Canadians, and a certain percentage of Canadians are Native people. But if they were underrepresented in my study, I wonder if there would be a way to reweight them so that it more accurately matched the population. I'm not sure if that's a stupid idea. I guess it would really depend on the situation.
Yeah, I don't know if there's any work, but that seems like a really interesting idea to me. The policy like reweighting, kind of like they do for the offline policy learning, because you never really get a distribution from the policy you're probably going to want to use. So you have to reweight it properly. I wonder if something like that could be done. But then I guess you'd also need like a good model of the average people you're targeting and then the Mechanical Turker ones to weight them properly.
But
Yeah.
I don't think that's too hard, right? Because you have census data. Like if you're just talking about, oh, I want to care about just North Americans in general, let's say, or Americans in general, right? You have census data and you have like, I guess like if you want to important sample, let's say ethnicity, for instance, you have census data for ethnicity and you might ask them to fill out a form of their ethnicity when the like Amazon Turks, go do their task. And then you could important sample based on that. That's actually a pretty interesting idea.
Yeah, and it's not just this ethnicity. You could think about, I mean, it's a dumb measure, but you could think about IQ. Better things would be thinking about backgrounds, levels of schooling, all of that.
Yeah.
And if you want a system to work well for the general population, then maybe you could kind of reweight re-rates your learning algorithm, or at least re-weights your results to say that, yes, Turk is biased. We got 0.45 out of 1. And we think if we were using the representative sample, we would have gotten 0.42 out of 1.
Does anyone know if there's any work done in like because I know there's a lot of like issues with the medical field where certain things will affect certain age groups more. Is there anything in like the medical field where they look at importance sampling in order to like counter this like data set imbalance, I guess? Sorry, this is completely off topic.
Well, there's a lot of studies that used propensity score matching in a similar manner to that. So if they have unbalanced cohorts, like it was a non-randomized trial, then they propensity match people in each cohort to try to determine that. So not exactly in the sense of like applying it to systems that are being used new, but in terms of looking retrospectively, they do that.
I see. Cool.
Yeah, and then when you obviously want to try to recruit cohorts that are similar for the different conditions, but I also remember that it used to be a lot of studies were performed on men, many more men than women, and I think now there's still many more studies are performed on white people. At least in the U.S., white people as opposed to ethnic minorities, and there could be changes there too. So it's you definitely want to train on the same population you care about. And this is really off topic, but I was listening to I think it was a Code Switch podcast, and how earlier in the class in the semester we talked about the Tuskegee experiment, where the U.S. government gave syphilis to a bunch of Black American men, I think, and that has had lasting impact on the African American community and their trust of doctors. So now when people are trying to recruit African Americans to test out COVID vaccines, and they have to work that much harder because they want to make sure that they get a representative group.
It's sort of interesting. Maybe there's room to create an AI system that certain groups of people trust more than established systems of humans.
Yeah. So if you can say, I don't trust the man, but I trust the machine. I trust the man that built the machine more than the government. Yeah.
So like the recidivism score, not the compass, the other one, the one like it's provable that it doesn't take race into account. And so I could easily see people trusting that system more than human judges potentially.
Yeah. So if you can get people to understand why the system is not biased, they may indeed trust it more. Interestingly, just yesterday, a colleague sent me a paper where they were talking about a very similar thing, saying that, let's say you have a protected class like ethnicity, you could remove it so that it's just not part of the data set. Or in some cases, if you include it in the data set, but have it flagged, you can actually work to come up with a more accurate system that doesn't take it into account in the end. So that explicitly reasoning over what you can't end up using could be better than just throwing it out. So I found that counterintuitive. But if you really can show that your system is not biased for race, for instance, and people believe you, then maybe they would trust that more than a human judge. Okay, so then in the paper, they started talking about mental models and how they basically had to figure out, the human participants needed to figure out whether they thought the AI was going to be right or not. And then they talked about updates. So there is the locally compatible update and the globally compatible update. And when I looked at the locally compatible update, it seems like you'd never be able to do that in practice. Maybe I misunderstood that. Did anyone drilling down into the locally compatible update, did anyone understand whether this was just an ideal example that you couldn't achieve, or is there a way that you could actually do this?
Sorry, Matt, do you mean locally compatible update?
Yes. Was I saying something different?
Uh,
Sorry.
not something else. I forgot what it was.
Yes, locally compatible update, the first definition.
How I understood it was, right, so basically so if your mental model agrees with your old model, then, oh, for all X, yeah, I guess that's not.
Because what I thought they were saying is let's look at for every input, we're going to see if your mental model agrees with the first H with the first classifier, then it has to agree with the new classifier. Is that the right?
Yeah, I was a bit confused by this too. It seemed to me like then there wasn't really an update done if it's like if it's also recommending the same action.
Well, I think they're saying that after an update's done, you still agree with you're still in agreement with your mental model.
Okay, here. So for every input where the user trusts the AI and the old AI recommends the correct action, the new AI also recommends the correct action. But it seems, so if you had a finite data set, then you could do this, but it seems like you would have to go through all possible inputs, and for all of the ones that the human trusted, then run this comparison.
I think maybe just a little further up where it says that if it does not introduce new errors, maybe then we can safely trust it. That might be the key thing. Yeah.
Okay, so let's say we had a 10-point data set, and the user trusted the AI, and the AI was correct on half of those instances. Then those 5 instances would also need to be correctly classified by the new AI. But if you don't have a finite data set, if you're just trying to say I can classify images as cancerous or not, it seems like you wouldn't be able to do this. Okay, so I'm not crazy. Good. So then that was the local compatible update. And then they go to the global compatible update, where it's basically locally compatible for any mental model. So they're saying that, actually, maybe someone else could try to say this more clearly than I'm mangling it.
Are they missing a subscript 1 in the predicate?
Yes, I think that should be H1.
Okay. So if you answer correctly for your first model, then you answer for all X, you answer correctly for your first model, then you answer correctly for your second model as well.
Okay. So this is, in some sense, this is simpler, because they're not even worrying about specific mental models, right? They're just saying if you were right before, you need to be right now. But again, if you don't have a finite data set, that you can't really test that. So I guess they must be assuming you have a given fixed data set.
Yeah, it seems like this is in the supervised setting, and they're trying to get like an update rule that is like compatible in one of these cases, right? So
it seems like it wouldn't be applicable to their 2 examples of patient readmission and recidivism.
why is that?
Because you can't know for all X for either of those cases. You can't know that in advance.
Yeah. So if you phrased it as we are going to look at all past data for which we have labels and see if any of the ones that the old classifier got right, if the new classifier gets it wrong. Maybe that's what could be what they mean.
It sounds like they're describing how to overfit.
So, okay, why do you say that?
Well, they just seem to be, it's like all you're doing is you keep iterating on the same validation and test set together. You would be doing it over and over if you're just always trying to get the same positive results.
But I don't think correctness is what they're going for here. They're looking at globally compatible updates. So they're looking at updates that are safe, essentially, right? That still agree with a previous mental model. So it doesn't really, they're not talking about I guess it's a weird definition for all X, right? Maybe they should have done something along the lines of in expectation instead, because that'd be a bit more, plausible, because you can take samples of an expectation. But yeah, for all X is a bit suspect, I guess.
Yeah, so it means you have to be able to go over, iterate over all of your past data, and your classifier, the new classifier, does no worse on the examples you got right before. So go ahead, Graham.
I like their term backward compatible in it. Just the idea that you're not, anything that you got right before needs to stay right. And also their little example of the 95% accuracy for some kind of medical thing, and it predicts very well on the elderly. If an update puts it up to 98% accuracy, but now all of its mistakes are in the elderly, then the human using this already has their mental model of it works well on the elderly, and this new update makes it so it specifically does not work well on the elderly. They're going to use it incorrectly because they've learned to trust on the elderly and maybe do their own stuff for edge cases or whatever.
Yeah, I think that's a good motivating example. And part of it comes down to whether you care about the elderly or not.
Yeah, another thing that just came to mind that I came up with a contradiction again with, but I was thinking maybe it would be logical to just consider maybe the last 100 most recent examples, because that's kind of what a human remembers maybe of interacting with the AI, and that's what it understands that it's good at. And so as long as you don't break those, or you're still getting the correct ones, you're keeping the same correct classifications there for the past 100, then you might be okay. But then I think it was mentioned, I just remember there was kind of mentioned in the discussion or something about the catastrophic forgetting problem, in the sense that maybe as a human, and I don't know if that's exactly what they meant, but so what I thought of is maybe in the case of a human, you'll kind of test out this AI, or maybe you would have been doing different styles of work before. So you had some impression on how it's going to perform, and for some classification in medical, I guess. And then maybe this month you just weren't working on that anymore, but you still know that the last month it performed well here. So if you update the model and you're just looking at the most recent classifications, then you're going to not worry about stuff in the past. And then a human that probably remembers all the history, and maybe this is why the Markovian stuff could be a bit tricky as well, I don't know. But if you remember all the history, then that becomes a problem, and you probably do want to consider all the past examples. That becomes kind of tricky too, right? Because you don't know as a human, and what's also a meaningful example, right? Because it might just be one example that was specifically interesting to a human that the AI got really right before, and that's very valuable, and it always is kind of in memory for the human. So I think it becomes really tricky as to what you should not consider.
Yeah, and we want to minimize confusion by switching. We don't want the system to suddenly start getting things wrong. But if we're going to improve, we probably can't be strictly globally compatible all the time. We probably want some trade-offs. So we could reduce the emphasis on this global compatibility. We could do things like emphasize the more recently seen examples more, and lower the weight of very long ago samples. We could also think that some people are more important than others. That's a bad example. Well, no, because we know that, no, that's too political. You could have seen an example recently in the US where a certain individual got very special medical treatment that was very expensive. And not everyone has access to that same treatment, but you could say that that person was more important and the system should be more likely to work on someone like that, which is awful when I say that out loud. But I think someone else was going to say something. David, did you have a comment?
Sorry, this was kind of related to what we were talking about before, and also this whole forgetting thing.
Mhm.
I think like the whole for all x thing is everything in your data set, because that's kind of the point of the paper, right? The point of the paper is to not forget and to like have this extra dissonance term that's like a regularizer that basically penalizes you if you forget something, but doesn't penalize you. Well, you have a lower loss. You have if you remember what you had before. So I guess the whole, like, it does make sense, their formulation. It's just to like remember what they saw before so that an update doesn't ruin that and your trust remains in the system.
Yeah, I think I buy that. Well, and the pretty soon we'll start talking about their solution, but their solution may not be optimal, but they do show that their solution gets better performance than just kind of ignoring this.
Yeah, sorry. Maybe I didn't understand. What was the real issue with this globally compatible update? It was the fact that there would be too much examples to go over to make sure that they're all okay, or that you didn't break anything for any of them. Was that the issue?
Yeah. So if you just look at the training data you've collected so far and run over all those instances, then you're fine. What I was getting confused about is I'm used to, when I evaluate a function approximator, I don't care about the examples I've already seen. I care about the examples I'm going to see. I want to see how it generalizes to new things. And that's not the point of what this is doing. The point of this is explicitly only looking at past instances. I think that's what was confusing me.
Yeah, I think that's good. But maybe the thing that I understood is the model that's already being introduced with the update has kind of been decided on as a better generalization, right? And then this is like a step to look back and make sure you're still doing okay on the past examples. So like, because there's an update occurring, doesn't that already kind of guarantee that the model is better? And this is just like to double check that you're not hurting anything.
I don't think so, because with this additional constraint, right, you're limiting well, I'm guessing they're using some neural network of some sort here, but you're limiting your like function approximator more. So that means your generalizability abilities are less. So I guess it's more about like taking safe steps towards better results, if anything. At least that's how I understood like what they were trying to do.
Yeah, I think that's a good way of saying it. So they've got this loss function that's going to think about, how do I improve accuracy while trying not to hurt places I was correct in the past. So it is essentially constraining how you're going to climb a gradient. And another point here is I think they're looking at categorical results. So is the classifier right or not? You could think of this in a regression setting as well, where, if I predict a 1 and 1 is right, but I predict a 1.1, maybe that's fine. So that could be an extra level of complexity you could think about too. Okay, so they've got this compatibility score, which is so looking at over our past data, how does the new thing shift or make us worse over the things we got right? And then they go and actually make a loss function, where they get equations 2 through 5, ultimately trying to trade off dissonance, which is related to compatibility and the prediction, the accuracy. So presumably then you could trade off between the two, and depending on the situation. So for instance, if the accuracy was really bad, maybe it doesn't matter if you suddenly reverse a bunch of things that you got right in the past, because you were just doing so poorly in general. Like the overall team's performance was so bad, you just want to get out of that area, get the AI to improve as fast as possible, and then worry about maximizing the team score. That I don't believe they discussed that. I'm just making that up. Does that kind of make sense, that you might want to change this over time? Okay, so then they say we've got this standard platform, and then we're going to give them the payout matrix. So they say if the AI is right and you accept it, you get 4 cents. If the AI is wrong and you accept it, you lose 16 cents. Or you could say, I don't trust the AI, and you get a 0. And then I think somebody already mentioned that they really liked the Q&A nature of the experiments. Does anyone want to comment on that writing trick? So I bring it up because yesterday there was a discussion on Slack about a paper where they had a section that was titled something like warm up. So before they got into the serious derivations, they were going to do the simple one. So which is really nice, right? Because it gets you going, but is also kind of intimidating. And here, and I like this rhetorical device. So in the experiments, they basically say, here's a hypothesis, here's a question. Now let's run an experiment and show you the result. So it's kind of a way of walking you through and making it really clear why they were running the different experiments, rather than saying, here are 5 graphs, now I'm going to untangle what they all mean. Another paper I saw recently that I really liked had an experimental section, and then I think it was still in the experimental section, or it might have been in the discussion, they had a frequently asked questions section. So I'm not sure whether they were just dreaming these up as things that people might be interested, or if they had submitted this paper multiple times, the reviewers kept being jerks, and they're like, okay, we're going to spell this out for you so you don't miss it. But I kind of like it when people get creative. So here they were saying, question 1, do better mental models of AI lead to higher team performance? And then they can go and really nail down exactly what they're claiming. Oh, one question. I'm wondering if anyone picked this up. So the basic idea is they have 4 different settings. The first one is the AI doesn't change at all. And then the second setting was where the AI gets better and is compatible, or the AI gets better and is incompatible. But there's a 4th setting too. What am I missing?
I think there's multiple ways in which it gets better. So there's it gets, or maybe you said the 2 that I was thinking.
No, okay. So there's same error boundary, and then compatible error boundary. I think I was lumping those together. So the same error boundary group receives an update improving accuracy, and the boundary is unchanged. And then in the compatible error boundary, the number of features changes from 2 to 3. So they're changing the setting more. One thing I couldn't figure out is whether this change was announced or not. So they run for 150 cycles, and at 75, in 3 of the 4 cases, they update the AI. And I couldn't tell in those cases, do they announce to the person, you have a new AI partner? Because there could be a pretty big difference between someone being like, whoa, something just went wrong, versus announcing that now you've got an update. Because I imagine it would take you longer to kind of notice that type of concept drift if there was one. Okay, and basically they show it works in their toy example, and then they show some high stakes domains. Oh, and the nice thing they do is they show that, well, but if we're just trying to improve accuracy, that does not ensure compatibility. Because one thing a reviewer might ask is, okay, you've got this compatibility thing. How do we know that doesn't just drop out of existing methods? But here they empirically show that not only is compatibility important, but that existing methods do not necessarily do well on this metric. So I thought that was cool. The other thing I was trying to think about is whether you could have an idea of compatible updates in a reinforcement learning setting. So I was trying to say, okay, if let's say I was in a finite state space and I had states that and I could tell when I learned the optimal action in a state. Could I do something like I only update my neural network in a way that I don't start taking suboptimal actions in states where I had learned optimal policies? But I wasn't sure if that made any sense.
I guess, so that's like, as soon as you reach optimum, no more exploration. Seems good until the environment changes in any way. Because I thought one of the nice things about RL was that you get something to kind of learn the gist of what is a correct solution. And then if you change some walls in your map, then it can still figure stuff out because it's always got a little bit of exploration in it.
Absolutely. So if the environment is non-stationary, then you better keep exploring. But also like you were saying, if you learn the optimal, that's great. Unfortunately, in most settings, you don't actually know whether you've learned the optimal action. So my suggestion of never unlearning optimal actions predicates you on being able to identify what those are. No, I can't think of any. I got super excited about this, but I don't think there's any way to directly apply it to reinforcement learning.
Unless there's ways to have checkpoints, like you can, like in math, they always like doing upper bound, lower bound stuff. So if you can say that, there's a lower bound, we can't possibly get to some checkpoint faster than this, and then you actually get to it in that amount of time, then you just say, never change any of that. That's all optimal.
I guess there's also something that's kind of related, which is in the realm of like the AI safety, the RL safety literature. But I guess it's not so much as like remembering what was good, but just not doing what's bad, if anything, right?
Yeah. Yeah, trying to avoid critical states or trying to avoid bad things. But I think the key insight here was saying I'm going to memorize past data and not do worse. So if you could update your policy so that you would have taken different actions on states you had visited, but I don't see an easy way for you to evaluate whether those different actions would be better or worse than the actions you actually took, unless you had already finished learning and solved the entire MDP. I think David's talking, but I don't hear him.
Hello?
Yeah, now I do.
Oh, there we go. Sorry, I think I unplugged there for a bit. I think that's what the policy improvement theorem kind of is, right? Like in the tabular setting, like you always improve because your action value functions always you're always taking the max of them whenever you do like iterate, whenever you improve and then evaluate. But in like the function approximation setting, I don't think it's possible to make these kind of guarantees that like, oh, my actions are definitely going to get better because, you know, if you change one action, like let's say to left instead of right, then you're going to change something else because you're doing function approximation, right? And that like one thing goes down, another thing might go up.
Yeah.
I do wonder if the constraint of if you got it right before, don't ever get it wrong again is too strong in the sense that it might be very difficult to follow that gradient to ever get new things right. I'm wondering if it would be better to consider something like you have some threshold and don't ever do worse by this amount in a category, but just because you got, you know, data point 6 right before, it doesn't have to be right again as long as you're still at 80% in the category that it's in. Like there's a general improvement of X% and no particular category dropped by more than, and then some other threshold.
But I feel like that's like, because the whole point of this paper and like doing it that way was because our mental model still aligns with our expectations still aligns with what we think the model is going to do. Whereas if you just say don't go below a threshold, right? Like you could do that. You could do that anyway.
I think, or at least I thought equation 5 was kind of doing that, was trading off how many of these past instances that you did get right, you could get wrong, trading that off with the improvement in accuracy. So if you could say, well, I'm no longer going to get Matt's cancer recommendation right, but I improve accuracy by 5%, maybe that is worth it. Or what Graham, I think you might have just been suggesting also is maybe if I get Matt's treatment wrong, but I get Nick's treatment right, and if in some way they are the same grouping, then maybe that's fine. So we don't want to get all old people wrong, but maybe if we don't get the old people in expectation any worse, maybe that's fine.
Yeah, treat people from the same category as interchangeable so that it's not one of them isn't, I can't think of an elegant way of saying that at all, but like not like as a scantron, but more like group them as distributions instead.
Yeah, stop thinking of people as people.
I guess it also depends on your like task, because like let's say you're a doctor treating individual people, like you're not going to be able to differentiate the two because you need to treat this individual person, and seeing your algorithm get it wrong for this individual person is kind of like, oh, like what? But then for other examples where, you know, experts look at groups of people, that actually might not be a bad idea, I guess.
It might be adequate instead of trying to determine whether you're going to get it right or wrong, and then only updating or only doing it if you're, you know, going to keep getting it right. If you just warn the user, like, I mean, you would have to categorize, but you'd warn the user, with this update, I may do worse on elderly people.
Yeah, and that's actually one of the things the authors mentioned. If they could describe the kinds of changes, or if they had accurate confidence scores, those could be ways of mitigating this risk.
Yeah, something that came to mind is if this kind of like using this type of loss restricts like the possible set of gradient paths in a sense, like Graham was bringing up. I wonder if another option is to like kind of train your models like you would without like with whatever loss you wanted to normally, and then just use kind of this global compatibility as a method to know if you're okay with introducing this upgraded model. So like imagine you train like another model and with some other loss, and then you're like, okay, this does better than all my other models. Now let's see if this is acceptable to introduce. And the way I decide that is whether it performs correctly on all the past examples that this old model did, and then obviously it's better because it got better performance. So then I'm limited by this path of this loss that was defined here.
Yeah, so if you had this two-step process where you could optimize in an unconstrained way and then verify you've not broken anything. The problem is you probably are going to break something. Because they showed that existing methods typically do not achieve this. And if you want to minimize the chance that you break something, then you probably want to be constrained in your search. But you're absolutely right. It's going to be some kind of a trade-off that's going to be problem dependent. All right. The final thing I wanted to mention was that I like the future work where they talk about better understanding cognitive models and how people create and update those mental models. So that's you might remember that could be related to what Delaney was proposing with her intelligent tutoring system, where she was modeling what people know. And if we could get better ways of modeling people, hopefully we could do an even better job or come up with other ways of, in addition to compatibility, maybe there are other ways of updating a machine learning model that doesn't impact the overall system performance so much. All right, so we are out of time, but thank you for helping me ramble through this paper. I thought it was pretty cool. So pat on the back to me for suggesting it. But I thought the other paper was cool too. So hopefully you did get a chance to read it. Remember for Tuesday that you have to read the depressing paper. And also exercise 3 should be up soon. So have a great weekend, everyone.
See you.